If you're an ANSYS Fluent user, you may have wondered what the difference is between the enhanced wall functions and the standard wall functions are that ANSYS Fluent offer when you're in the case setup. Well, if you have wondered that, in today's talk, I'm going to be going through a comparison of the enhanced wall functions and the standard wall functions. And by the end of the talk, you should have a really good idea of actually what the differences are between the two methods and what the CFD code is actually doing behind the scenes when you select them. So if you're interested in the enhanced wall functions, sit back, take some notes, and here we go. So just to start with a quick overview of what I'm going to talk about today, I'm going to start by going through how wall functions work in general. So that will mostly be a recap video of what I covered before in my previous wall functions video. I'm then going to look at standard wall functions in ANSYS Fluent, and that will allow us to compare the standard wall functions to the enhanced wall functions in ANSYS Fluent, which I'll go through later. And then finally, I'm going to finish off by quickly summarizing when should you choose to use enhanced wall functions and when should you choose to use standard wall functions. So before we begin, it's worth noting that standard wall functions are used by all CFD codes. They have to be included in CFD codes if you're going to be solving RAN's turbulent flows at all. You have to have wall functions in your CFD code. So all CFD codes will use them. However, the nomenclature of using enhanced wall functions is specific to ANSYS Fluent. So other CFD codes may choose to do different things, but the enhanced wall functions is specific to ANSYS Fluent. And if you look through the Fluent manual, you'll see that ANSYS Fluent also offers enhanced wall treatment for the K epsilon model. And I'm not going to be talking about enhanced wall treatment today. I'm only going to be talking about enhanced wall functions. The enhanced wall treatment will be considered in another video. So to start things off, just with a quick recap of what wall functions are and how do they work. Now, the first and most important thing to appreciate is that in finite volume CFD codes, the flow variables always vary linearly across the cells in the CFD mesh. So that's all of the variables, that's velocity, temperature, pressure. The flow variables always vary linearly across the cells. And in most CFD codes, the variables are stored at the cell centroid. So we'll know the velocity, temperature, and pressure at the cell centroid. That's what the CFD code solves for. And then the variable varies linearly across the cell around that centroid. And you can see that in the diagram there. It doesn't matter what the shape of the cell is, the flow variable will always vary across the cells, and that's true for all cells in the mesh. And of course, if you had a node-based CFD code, which is more uncommon, the flow variables would still vary linearly. However, it would be about the nodes rather than about the centroids. Now, at the wall, this linear variation of the flow variables can cause a problem. And the reason for that is that if the cell at the wall is too large, then the CFD code, of course, will show a linear variation of flow variables between the wall and the centroid. It has to. CFD codes, the flow variables always vary linearly. However, we know from observations of the flow field that the real velocity profile between the centroid and the wall will be non-linear if the cell is too big. And going back to theory, remember, of course, if the cell is within the viscous sublayer, then we know that the velocity does vary linearly, and that's fine. However, if the cell is too large and the cell is actually in the logarithmic region or the outer region of the boundary layer, then we know that, of course, the flow profile does not vary linearly between the centroid and the wall. And this will introduce an error into the CFD code if we don't account for this. The real profile is varying non-linearly, but the CFD code can only account for linear flow profiles. So we have to do something or there'll be an error. And the way we do that is through the action of the wall shear stress. Now, it's a common misconception that with wall functions, what the CFD code is doing is forcibly including a logarithmic profile between the cell centroid and the wall. It's important to remember that that is not true. CFD codes can only show a linear variation of flow variables between the wall and the cell centroid. So we're not forcing the velocity profile between the wall and the cell centroid. The CFD code actually does something slightly different, and that's to do with the calculation of the wall shear stress. So as a quick reminder for all of you, the wall shear stress is given by the product of the viscosity and the velocity gradient at the wall. So that's just an important formula to remember. I like to say it in words because it's a lot easier to remember. It's the viscosity multiplied by the velocity gradient at the wall. And what you can see from the diagram there is with the solid red line, I've got the real velocity profile, which of course is non-linear if our cell is too big, and the CFD velocity profile is with the dashed line there, which is linear because it has to be. And of course, what you can see here is that the velocity gradient at the wall with the CFD code will be incorrect because it can only account for linear profiles across cells. And the velocity gradient at the wall is going to be wrong. And what the CFD code will do is that in order to calculate the correct wall shear stress, it's going to modify the viscosity instead. So the idea is that the velocity gradient is wrong, but if we modify the viscosity, then the product of those two terms will give the correct wall shear stress. That's the idea behind wall functions. We're correcting the viscosity at the wall because the velocity profile is wrong. But if we get the wall shear stress correct, that means the forces and the heat transfer and everything on the surface of our body will still be correct and will give us the correct overall balance. So the principle behind wall functions and wall treatments is how we modify the viscosity at the wall to correct for the velocity gradient. And just as a reminder, if we think about the wall shear stress in terms of mathematics, what's the equation for the wall shear stress? We're going to use equation 2. So the wall shear stress in general, in any situation, is going to be minus, remember the wall shear stress acts in the opposite direction to the velocity profile, so there's a minus sign in there. And we've got rho, the density, times nu, the kinematic viscosity, times the velocity gradient at the wall, y equals to 0. And throughout this talk, I'm going to be, rather than using the dynamic viscosity U, I'm going to be using the product of the density and the kinematic viscosity because it's easier in the maths that follows. So equation 2 is general. That's always the wall shear stress. It doesn't matter real or CFD. The wall shear stress is always given by equation 2. Now, for the CFD cell, the velocity profile is linear. And that means that the velocity gradient is going to be UP divided by YP. So UP being the velocity at the cell centroid and YP being the distance between the cell centroid and the wall. So change in velocity over distance would be the velocity gradient, and it's linear. Now, what you can see there is that I've put a subscript W on the kinematic viscosity. And the reason for this is that this term is called the effective or wall kinematic viscosity, and the subscript W I've put in there as a reminder that this is the modified viscosity. We're changing the viscosity to account for the velocity gradient being incorrect. And what the wall function focuses on is how do we define what that new W is? How do we specify what the velocity gradient is? Specify what the kinematic viscosity is to correct the velocity gradient. And as further proof that this is actually what CFD codes do, as a reminder, we're correcting the kinematic viscosity on the faces of the cells that are in contact with the wall. And the reason for that is that we may have a cell where multiple faces are connected to different walls. So if you think of this cell that I've shown you there on the slide, this is a rectangular cell that's in the corner of the domain. You can see that the cell actually has two faces that are in contact with walls. And of course, each of those faces will have a different wall distance and a different y plus and a different velocity profile. And so the way that we can account for this is by modifying the viscosity on the faces of those cells differently. So we're always talking about the viscosity modification on the face of the cell in contact with the wall. So now the big question remains, how do we modify the viscosity? And this is where the wall functions come in. There are different methods of modifying the viscosity. So the way we're going to do this is by, let's say that the real velocity profile between the wall and the cell centroid is given by some function. U plus is some function of y plus. That's equation 4. So I'm going to do this derivation completely generally because it doesn't matter. So it doesn't matter what form of that velocity profile I choose. But to help you understand, because that can be a bit of an abstract equation there, an example of what the velocity profile might be is the logarithmic profile. So 1 over kappa log EY plus. That might be something you've seen before. So this velocity profile is completely general. It doesn't matter what it is at the moment, but it's likely to be something like the U plus is 1 over kappa log EY plus. So we're starting this derivation with a general form of the velocity profile. U is some function of y plus, and we're going to be deriving a modified kinematic viscosity to correct the wall shear stress. So in this derivation is key for all wall functions and your understanding. And for those of you who've been through part 2 of my fundamentals course, you will have seen this derivation before and you will be used to it by now. But for those of you who haven't, I'd highly recommend going through the derivation yourself because it can be quite confusing, and it will really help your understanding if you actually go through the derivation. So the key part of this derivation for the modified wall viscosity is to write U plus is equal to U, that's the velocity at the cell centroid, divided by the friction velocity U tau, because that's the definition of U plus. And the trick in the derivation is to multiply top and bottom by U tau. So you've got the U tau squared on the bottom and U tau on the bottom. And then from the definition of U tau, the friction velocity, we can substitute in the wall shear stress there to arrive at equation 7. And that's the key part of the derivation. That's always missed out in the majority of the sources that you see. That key part in the derivation is missed out, and it took me a long time to work out exactly what it was. So definitely make a note of that one. And if we now take equation 7, we can rewrite equation 7 in equation 8, and that now gives us an equation for the wall shear stress. So the wall shear stress is minus, and then you've got the U tau rho on the top, and then the function of y plus on the bottom. So as a reminder, equation 8 is general. We haven't specified yet what form the velocity profile takes, and it may be quite confusing because we've got these concepts like U tau and y plus floating around at the moment, but that will become clearer later. And I'd highly recommend just doing that little bit of algebra for yourself, just so you can see how we get out the wall shear stress in there. We're not going to be doing any differentiation or anything. That's definitely a trap that I fell into, just rearranging the definitions. So we take equation 8, that's the real wall shear stress that we know is acting on the wall. And then what we're going to do is equate that with the CFD computed wall shear stress so that we can then rearrange to see how we correct it. So the wall shear stress in the CFD code is given by equation 9 there. Remember, we looked at this before. We've got minus rho and then nu sub w. This is the effective kinematic viscosity that we want to know what it is. That's our solution. And then multiplied by up over yp. That's the velocity gradient that's incorrect. And so now equation 9 and equation 10, we've got an equation for the real wall shear stress and the wall shear stress in the CFD code. And for the CFD code to be correct, we're going to equate equation 9 and equation 10 and then rearrange for nu sub w. So if we do the rearrangement, we arrive at equation 11 at the bottom. And what equation 11 says for us physically is that if we modify the kinematic viscosity on the face of the cell using equation 11, that will mean that when we run the CFD code, the wall shear stress that we compute will be correct, even though the velocity gradient, which is linear, it has to be, is wrong. So that is what equation 11 actually means. And so far, we haven't specified what f of y plus actually is. And this is where the different forms of the wall functions come in. So just to summarize, we've got equation 12 there, which is our key equation that we're going to be using for all of this talk. And that is the effective wall viscosity there, nu w, is equal to nu, that's the kinematic molecular viscosity, that's the material property of the fluid, multiplied by y plus over the f of y plus. And straight away, what we can see from equation 12 is that nu w is going to be increased above nu. So if that term in brackets is greater than 1, which it always is, then what we're doing physically is we're increasing the velocity on that face so that because our velocity gradient, which is linear, is too low, the product, which is the wall shear stress, will be increased. So we're accounting for our incorrect velocity gradient. And equation 12 is valid for both the standard wall functions that are used in ANSYS Fluent and the enhanced wall functions. We're now going to move on to look at the difference between the standard and the enhanced wall functions. So starting with the standard wall functions, the way that the standard wall functions work is the equation for f of y plus. And this is one that you'll be used to if you saw my previous talk and if you've looked at wall functions in general on the internet or in various CFD textbooks. You'll find something like the form of equation 15. So u plus will be equal to y plus when y plus is less than 11.25. That's when we're in the viscous sublayer. And u plus will be equal to 1 over kappa log ey plus when y plus is greater than 11.25. That's in the logarithmic region. So how does this look? So you might be familiar with this plot for standard wall functions. I've got the standard wall functions with the dashed line there, and then I've also got DNS data as a comparison with the solid black line. And as a reminder for this plot, we've got y plus on the x-axis and u plus on the y-axis, and of course the y plus axis is logarithmic. And what we see is that u plus equal to y plus, so that we have the viscous sublayer solution at the start, and then at the crossover point of 11.25 the function switches over to the logarithmic form, which on these axes looks linear in the logarithmic region. And this is the standard wall function that's used in ANSYS Fluent. And what you can see is that actually the standard wall functions do a good job in the viscous sublayer when y plus is less than 5 and in the logarithmic region when y plus is greater than 30. And this is why when creating meshes for CFD, it's often recommended to ensure that your y plus is either less than 5 or more than 30 if you're using the standard wall functions. It's to avoid this error, which you can see in the red shaded region in the buffer region. So that's how the standard wall functions work. But as a reminder, the one bit which you may have missed out on, which is often not explained in the literature, is that of course the way this is implemented in the CFD code is by modifying that effective wall viscosity. So if we substitute in f of y plus into equation 14 here, so we substitute in f of y plus, what we arrive at is equation 17. And what you can see here is that the effective wall viscosity is just equal to the kinematic viscosity in the viscous sublayer. And this is exactly what we expect. The top line there is exactly what we expect. If our cell is very small, we're in the viscous sublayer and our effective wall viscosity is correct because the velocity profile is linear between the cell centroid and the wall. However, if we're in the logarithmic region, then remember the real velocity profile is logarithmic. The CFD code can only simulate a linear velocity profile, and so we correct the near wall kinematic viscosity with that bottom equation which you can see here. And if you plot it, then you'll get something which looks like the figure I've got for you there on the slide, where the dashed line are the standard wall functions and the red line is the DNS data. And what you can see is that actually for the DNS data, the standard wall functions give an excellent match in the viscous sublayer and in the logarithmic region. But again, there's this error in the buffer region between 5 and 30. And that's where the enhanced wall functions come in. It's an approach that tries to minimize and reduce this error with a better approach. So for the enhanced wall functions, what we're going to do is use a different function for f of y plus. So not the profile that we used before. And the profile that's used by ANSYS Fluent is given in the user manual, and it's given by equation 19 there. And if you may not have seen this equation before, but if you go and look in the user manual, you'll find it. What you've got is you've got this e to the gamma term. So e to the gamma multiplied by a u plus laminar, and then an e to the 1 over gamma times the u plus turbulent. And so what does this mean? What is this enhanced wall function? What is it? Well, firstly, you can see that there's no conditional statement. There's no if statement to show you you should use a particular function for a y plus of less than 11.25 or greater than. It's one continuous function that's valid for all y plus. And what this e to the gamma and e to the 1 over gamma are is they're a blending function that smoothly blends between the U plus laminar and the U plus turbulent. So the way to understand this, if you look at it, is with the enhanced wall functions, we've got the laminar solution, U plus laminar, and we've got the turbulent solution, U plus turbulent, and we're using this e to the gamma function to blend between them. So we're not going to have that abrupt change. It's going to be a smooth blend. And if you're interested in this blending function and where it comes from an original paper by Kader, which I've also linked in the description for this video. So you can always go and have a look at that blending function if you want to see how they came up with it. But what I've got for you here is, rather than looking it up, is I've just got a plot of that blending function so that you understand actually what it is. And I've got e to the gamma in solid red and e to the 1 over gamma with the dashed red line. And as a reminder, e to the gamma is multiplied to the laminar solution, and then the e to the 1 over gamma is multiplied by that turbulent solution in the logarithmic region. And what you'll see is that from the plots of the blending functions, we're going to be using entirely the laminar solution when y plus is less than 2, let's say, at the left end of that plot. And then as we move through the buffer region, the blending functions are smoothly going to blend between those solutions until when y plus is greater than 30, we're using almost entirely the turbulent solution. And I'd highly encourage you to plot these blending functions for yourself just to have a look. It really helps your understanding. But one thing you'll notice, of course, is that the blending is not symmetric, and that's because of the weighting that's needed for the different functions. But I'm not going to go into any more detail. It's more useful for you to either read the paper or to have a go at plotting the functions for yourself. So now, what does this enhanced wall function look like? Well, it's a blend between the laminar solution and the turbulent solution. And what I've got for you here is a plot of the enhanced wall function with the solid red line. And what you can see straight away is that the enhanced wall function is not perfectly smooth. There are some bumps in it, and that's because the blending function is not symmetric. And we've got the solid black line, which is the DNS, which is what we're trying to reproduce. And what you can see straight away is that definitely the enhanced wall function is a lot closer to the DNS data than the standard wall functions are. So in that buffer region between a y plus of say 5 and 30, the enhanced wall functions definitely do a much better job than the standard wall functions. And this is why the enhanced wall functions are often recommended in CFD simulations. It's because if your cell happens to have a y plus between 5 and 30, if you used the standard wall function, you'd be a long way off and you're likely to get the wrong result for those cells. But if you use the enhanced wall functions, you're going to get a lot closer to the DNS data. It's not necessarily perfect, but you are definitely closer with the enhanced wall functions. So before I move on, it's worth just noting that there are those wiggles in the enhanced wall function treatment. And straight away from looking at that plot, you might think, why don't we just use a better fit? We did the formulation for the wall functions completely generally. We've got that f of y plus. Why don't we just use a polynomial fit, say, and get as close as we can to that black line? Why are we using this weird e to the gamma function that doesn't really give a good match? Well, I'm going to go through that a bit later in the talk. So before I move on, I really want to remind you all, of course, that even though that is the form of the blending, that's the form of the enhanced wall functions, if you plot it, if you plot u plus against y plus, remember that's not how it's implemented in the CFD code. We're not putting a velocity profile between the wall and the cell centroid. What we're doing is modifying that near wall viscosity. And so if you substitute in f of y plus, you get equation 20. And you can plot equation 20 and you'll get the plot which you can see there on the slide. And I've got the standard wall functions with the black dashed line, the DNS data in red, and then the enhanced wall functions in blue. And what you can see is that straight away in the viscous sublayer, so for very small y pluses less than 2, all three methods give almost identical solutions. And likewise, for y plus greater than 30, all three methods give very good agreement. So straight away from this, you can see that if you're using standard wall functions or enhanced wall functions, if your y plus is say 1 or if it's more than 30, it doesn't really matter which method you use. All the methods are going to give you very close agreement for the results. The only differences come in here in the buffer region with y plus between say 5 and 30, which I've got shaded in grey there. And the enhanced wall functions do a better job. The kinematic viscosity is much closer, but it's still not exactly there. And there is a bump close to y plus of 5, for example. And this is often why, if you look at the user manuals, why ANSYS and others recommend that you try and keep your y plus below 2 if you're using enhanced wall functions. So if you are, that's fine, but it's just worth being aware that if you're in the buffer region between a y plus of 5 and 30, you're never likely to get exact agreement with the DNS data regardless of what method you choose. So always bear that in mind. So now let's look back at this enhanced wall function that ANSYS are using. You've got the f of y plus is e to the gamma times the laminar solution plus e to the 1 over gamma times the turbulent solution. And the U plus laminar and U plus turbulent are the viscous sublayer and log law region profiles that we saw before. So they're equation 22 and 23. And we've got this e to the gamma and e to the 1 over gamma that's going to blend those two profiles together as you move through the buffer region. And the question still remains, why do we use this e to the gamma? Why couldn't we just say f of y plus is going to be some polynomial? So a y plus b y plus squared plus c y plus cubed plus, why don't we just have a very long polynomial and get bang on the solution? Well, the reason for using this formulation is that it's general and we can actually modify the form of the laminar solution and the turbulent solution if we want. So if we use this blending function, we can actually change the laminar solution and the turbulent solution and still get a good match to the data for different cases. And don't worry if you're a bit confused, I'm going to go into that in a bit more detail now. So it turns out that if you have a high-speed compressible flow or a flow with an adverse pressure gradient, then that U plus laminar and the 1 over kappa log EY plus solution for the laminar and turbulent regions aren't very accurate, and you actually have to change the wall functions that you use to get a better match with the experimental data. And so ANSYS Fluent uses this form in equation 24 because it allows them to modify the laminar and the turbulent solution to account for compressible flows and adverse pressure gradients. And the functions can be more general, which you see there in equation 25 and equation 26. I'm not going to go into detail now for what those functions actually are, but for the moment it's just worth appreciating that the reason for using this e to the gamma and e to the 1 over gamma is so that the CFD code can modify the wall function if you have a compressible flow or a flow with adverse pressure gradients, and the CFD code will still get a good result for those flows. But that will take a lot of time to go into, and so I'm going to look at those in a later video. So just to summarize with some recommendations and some final points for the talk, the enhanced wall functions that are used in ANSYS Fluent do give a closer match to the DNS data than the standard wall functions in the buffer region. However, it's important to remember that no wall treatment, regardless of what you use, gives a reliable and close match to the DNS data in the buffer region. And so for that reason, even if you're using enhanced wall functions or standard wall functions, you should try to ensure that your y plus is less than 2 or greater than 30 in the regions that you care about, because any cells that have a y plus of say 10 or 15 are still likely to have a wall shear stress that's slightly incorrect because the model is not perfect. And the reason that ANSYS use that general form for the enhanced wall functions with the e to the gamma is so that those functions can be extended when you have a flow which is high-speed compressible or with an adverse pressure gradient, because the DNS data and the behavior near the wall is actually slightly different to what the standard wall functions use. So that brings me to the end of the talk. I hope all of you ANSYS Fluent users found this talk useful, and you've now got a better idea of actually what's going on behind the scenes in the CFD code when you select to use enhanced wall functions over standard wall functions when you do your case setup. Let me know how you found this talk. Did you find it useful? Would you like me to perhaps cover the extended treatment for the compressible flows and adverse pressure gradient flows? Or perhaps would you find it useful to maybe look at the enhanced wall treatment that's used for the K epsilon turbulence model by ANSYS Fluent, for example? So yeah, let me know how you found the talk and what you'd like to see from me in the future. Until next time, thank you very much for watching.